Assalamualaikum. Today's topic is heat exchanger based on the yellow books. So in the process industry, the transfer of heat between two fluids is generally done in heat exchanger. The most common type is in which the hot and cold fluid does not come into direct contact with each other, but are separated by a tube wall or a flat or curved surface. The most common type is the one-to-one exchanger. So the transfer of heat is from the hot fluid to the tube wall and then through the tube wall. So the transfer of heat from the hot fluid to the tube wall, we call it convection. Meanwhile, the transfer of heat within the tube wall or the plate, it is by conduction, and then by convection to the cold fluid. So the difference between conduction, convection, and radiation. So conduction occurs when the transfer of heat by direct contact, in this case, the wall or the tube surface, within the wall or the tube wall. Then the convection is the movement of heat by actual motion of matter. So in this case, the matter is the fluid. And the last one is radiation, is the transfer of energy with the help of electromagnetic wave. Double pipe heat exchanger is the simplest or concentric pipe exchanger where one fluid flows inside one pipe and the other fluid flows in the annular space between the two pipes. So the exchanger can be made from a pair of single length of pipe with fitting at the end, or from a number of pairs of pipe interconnected in series. This type of exchanger is useful mainly for small flow rate. So if a cold fluid in, and then the hot fluid counter current to the cold fluid. So if a larger flow are involved, so we will use a shell and tube exchanger, which is the most important type of exchanger used in the process industry. So in this exchanger, the flow are continuous. Many tubes in parallel are used, where one fluid flows inside this tube. The tube arranged in a bundle like this, enclosed in a single shell, and the other fluid flows outside the tube in the shell side. So the simplest shell and tube is for one pass and one shell pass and one tube pass, or we call it one-to-one counterflow exchanger, like this. And the cross baffle are used so that the fluid is forced to flow perpendicularly across the tube bank rather than parallel with it. The added turbulence due to the baffle will increase the shell side heat transfer coefficient. So this is the hot fluid going zigzag through the baffle. So this is a one pass only. Same as a cold fluid, only one pass. Then we have a shell and tube 1 to 2 exchanger. So this is a 1-2 parallel counterflow exchanger. The fluid on the tube side flow in two passes, and the shell side liquid flow in one pass. In the first pass of the tube side, the cold fluid is flowing counterflow to the hot shell side fluid. In the second pass of the tube side, the cold fluid flows in parallel or concurrent with the hot fluid. So this is a 1-2 exchanger. So the two here refer to the cold fluid. So this is the first pass, and this is the second pass for the cold fluid. But for the hot fluid, it's still a one pass. So 1-2 exchanger. Another one is a cross flow exchanger. When a gas such as A is being heated or cooled, a common device used is the cross flow heat exchanger. So one of the fluid, which is a liquid, flow inside through the tube, and the exterior gas flow across the tube, bundled by force or sometimes natural convection. The fluid inside the tube is considered to be unmixed since it is confined and cannot mix with any other stream. The second type of cross flow exchanger is typically used in air conditioning and space heating application. This this type, the gas flow across a thin tube bundle and is unmixed since it is confined in separate flow channel between the fin as it passes over the tube. Log mean temperature difference and correction factor. When the hot and cold fluid in a heat exchanger are in true countercurrent flow or in current flow, the log mean temperature difference should be used. This is a delta TLM equal to delta T2 minus delta T1 divided by ln delta T2 over delta T1. So where delta T2 is the temperature difference at one end of the exchanger and delta T1 at the other end. So this delta TLM here, log mean temperature difference, hold for a double pipe heat exchanger and a 1-to-1 exchanger with one shell pass and one tube pass in parallel or counter flow. So this is the limitation for this. Other than that, we need a correction factor. So the usual procedure is to use a correction factor. So that is so defined that when it is multiplied by delta TLM, the product is the correct mean temperature drop delta TM to use. So other than double pipe exchanger and a 1-to-1 exchanger, we need to calculate the FT, correction factor. In using the correction factor FT, it is immaterial whether the warmer fluid flows through the tube or the shell. The factor FT has been calculated for a 1-2 exchanger and shown in table 16.2-1A. The two dimensionless ratio are used as follow. So we calculate Z and Y. If you refer to this, the denominator is the same. Wait, no, not for this one. Okay, just follow the THI, THO. So THI here is referred to inlet temperature. THO is the outlet. O is outlet. TCI is for the cold fluid inlet. The 3CO is for the outlet of cold fluid. So it is in general, it's not recommended to use a heat exchanger if FT is less than the 0.75. So meaning it's not suitable, you need to change the shell and tube arrangement. Using the nomenclature of Y and Z, the delta TLM can be written as like this. When the equation for exchanger is Q equal to UA delta T, where delta TM equal to FT delta TLM. So delta TM is the correct mean temperature drop, equal to correction factor times log mean temperature difference. So this is why you need to calculate Z and Y. So Y is considered as the x-axis, Z is the line. So with these two value, Y and Z, we can determine the FT in the y-axis. Yeah, see y-axis. Okay, example 1 to 2 heat exchanger containing 1 shell pass in 2 tube passes heat 2.52 K from 21.1 to 54.4 degrees C by using hot water under pressure entering at 115.6 and leaving at 48.9. The outside surface area of the tube in the exchanger is A0 equal to 9.3 meter square. So the first thing you need to do is to draw the 1 to heat exchanger containing 1 shell pass and 2 tube passes. Identify the THI until TCO based on the question. Question A, calculate the mean temperature difference delta Tm in the exchanger and the overall heat transfer coefficient UO. For the same temperature by using a 2-4 exchanger, what would be the delta Tm? So identify the THI, THO, TCI, and TCO. So first making the heat balance on the cold water. Assuming CPM of water is 4.4187, the heat capacity. So TCO minus TCI is 33.3. So Q equal to MCP delta T. So we have 348,200 watts. The log mean temperature difference using equation 16.2-4 is 42.3. Either Kelvin or degree C, same. Now, next substituting each equation 16.2-2 and 16.2-3. So, meaning calculate the Z and Y because we need to find the correction factor. Why need to find the correction factor? Because this is a 1 to 2 heat exchanger. So from figure 16.2-1a, this figure, so Z is 0.352y, which is 1.1 to 2. So for 1 to 2 heat exchanger, then you need to use this one. So 0.345. Yeah, was here. Is it correct? 0.74. 16.2-1a. 16.2. Yeah, this one. 16.2. This one. Oh, this one. 1, 2. Okay, this one. 0.345 here, 2. Okay, here. Then we identify the FT, then calculate delta with delta TLM to get the true delta TM, which is 31.3 degree C. So arranging question 16.2-5 to solve for UO. And substituting the known values, we have UO equal to Q over A naught delta TM. 1196. So for the same temperature, but using a 2-4 exchanger. So for 2-4 exchanger, you need to use 16 point dash figure 16.2-1B. This is 1B. So delta DLM is the same, but Z and Y is the same as well, of course. We just set this value for, sorry, the graph is different. So 3, 4, 1, 0.34, 352, sorry, 35, 1. 2, 2, Z equal to 2. So you get 0.94. So delta TM for this case is 39.8. So hence in this case, 2-4 exchanger tell us more of the available temperature driving force. Better should be. Exercise, you can try this one. The log mean temperature difference was used in the equation Q equal to UA delta TLM in the design of heat exchanger. This form is convenient when the outlet temperature of the two fluids are known or can be determined by a heat balance. So when the temperature of the fluid leaving the exchanger are not known or given exchanger is to be used, a method called heat exchanger effectiveness is used, which does not involve any of the outlet temperature. The heat exchanger effectiveness is defined as the ratio of the actual rate of heat transfer in a given exchanger to the maximum possible amount of heat transfer if an infinite heat transfer area are available. So this is the temperature profile for the counterflow heat exchanger. So what does it mean? So the temperature high inlet goes into the system or the heat exchanger. So it experience reduction in temperature. So meaning THI is higher than THO. However, for the TCI is cold. So once it's enter the heat exchanger, the temperature will rise. So TCI is less than TCO. In this case, CH is more than CC. H stand for hot, C is cold. Heat balance for cold and hot fluid. We have Q equal to MCP delta T. This is for hot and the cold. Effectiveness if the hot or cold is the minimum. So epsilon CH. So from here, the denominator, the down here, below expression below is the same. Epsilon C mean THI minus TCI, but the nominator is different based on either it's a call or port. For a single pass counterflow exchanger, so epsilon is equal to 1 minus this equation. A is area, U is the U tadi. Heat transfer coefficient, UO. Then we have Cmin or Cmax. Next is define NTU as the number of transfer unit. So in this case, NTU equal to UA over Cmin. So both equations have been plotted in graphical form. So, okay. So we calculate NTU and calculate the Cmin over Cmax to identify the value of epsilon. So this is for the counterflow, this is for the parallel flow exchanger. Example, water flowing at a rate of 0.667 kg per second enter a countercurrent heat exchanger at 308 Kelvin and is heated by an oil stream entering at 383 Kelvin at a rate of 2.85 kg per second. With viscosity 1.89, the overall U, overall heat transfer coefficient, U is 300 and the area is 115 meters square. Calculate the heat transfer rate and the exit water temperature. So assuming that the exit water temperature is about 370 K, the CP for water at an average temperature of 308 plus 370 over 2 is 339 Kelvin. So is a 4 point, so temperature 339 refer to table A, appendix A2, identify the CP or heat capacity. Then MCP hash equal to C hash. So 2.85. So rate multiply with 1.89 times 103 equal to 5387. Next is to calculate MCPCC for the cold fluid. So since CC is the lowest value compared to CH, so automatically CC is equal to C min. Since CC is minimum, C min over Cmax is 0.519. So NTU equal to UA over C min. Yeah, using equation, figure 16.3-2A for a counterflow exchanger, epsilon is equal to 0.71. Then we can calculate for the Q using this equation. Since we know the epsilon already. So TCO is equal to 361.3 Kelvin. This is the equation. This is the this is the heat transfer rate, and this is the exit water temperature. So it start with assumption first. Assumption. Assuming the exit water temperature is 370 K, then you can calculate the average for CP. But the actual value for TCO is 361.3 Kelvin. After now is a design double pipe heat exchanger. After fermentation, a mixture of ethanol and water is sent to a small distillation column. At the top of the distillation column, 95% ethanol solution at 65 degrees C is produced at a flow rate of 3.5 kg per cycle. Your job is to design a double pipe heat exchanger that will cool the 95% ethanol mixture to 40 degrees C by using cooling water that is available at 10 degrees C. Assume an outlet temperature of the cooling water at 55 degrees C and only use schedule 40 pipe. Do not do viscosity correction for heat transfer coefficient, and the 95% ethanol solution will be pumped to the inside pipe. Okay. So this is the heat exchanger. Step 1, complete the energy balance and calculate the amount of cooling water. Given an average heat capacity of the 95% solution of 2.6 kilojoule per kg Kelvin, then the heat lost by the 95% ethanol would be 227.5 kilowatt. So 2.6 is given only. Assuming that a system is adiabatic, and then all the heat loss from the 95% ethanol solution will be gained by the cooling water. Thus, the mass flow rate of cooling water is equal to MCW. See, cooling water CW is 1.209 kg per second, where the average heat capacity of water is 4.181. So, in order to use the Q here, because this Q is for the ethanol, but here the calculation is for water. So need to assume the system is adiabatic, where all the heat loss from the 95% ethanol will be gained by the cooling water. That's why you can use Q here as a value for ethanol, no? Because of the assumption of adiabatic. Step 2, there's a 7th step overall. Calculate inner tube diameter and velocity. Given an average density of the 95% ethanol solution of at 16 kg per meter cube, estimating the inner tube velocity at 1 meter per second. To facilitate turbulence, the inner tube cross-sectional area and diameter are using this equation. In this equation, so 3.5 kg per second. So we assume velocity as 1 meter per second. This is talking about the inner tube. So we have the outer tube. This is the outer tube for the cold fluid. Then the inner tube for the hot fluid. So in between the hot fluid and the cold fluid, this is what we call a annulus. So diameter equal to D, then calculate for the cross-sectional area which you get from here. So the diameter is, this is based on velocity assumed to be 1 meter per second. So we get diameter for the inner tube is around 74 millimeter. But you need to refer to schedule 40 pipe in table appendix A5 lah. Table A5 I think. This suffice will suffice. The minimum nominal pipe size is 3 inches. So with this pipe just the inner diameter or area is 77.92 millimeter and 4.769 times 10 to the power negative 3 meter square, which is slightly larger than the 74 mm and 4.289 this value require above, so we will have to calculate the true velocity given the pipe size chosen. So this calculation here is based on the actual pipe size. Yeah, best where you get the pipe size from the schedule 40. So based on the true design dimension from the schedule 40, we found that velocity V is 0.9 meter per second, which is slightly lower than the assumption 1 meter per second. Step 3, choose an outer tube diameter and calculate the velocity. Logically, the outer pipe must have a larger diameter than the inside pipe. So choose 4 inches. This is based on schedule 40. Since we know the inner tube, so outer tube no need to do the assumption for the velocity. Just choose a tube that is slightly larger than the inner tube, so that there's a annulus with an inside diameter of 102 mm, outside diameter 114.3 mm. The cross-sectional area available for flow in the annulus, so annulus is between the outer tube and the inner tube, the space between these two tubes. So in this case, pi over 4, 102.3, which is the inside diameter of the outer tube. 88.9 millimeter is the outside diameter of the inner tube. So we have a 2.012 and 10 to the power of negative 3 meter square. From this area and the calculated flow rate of the cooling water, rho equal to 996 kg per meter cube. The velocity of the water is VCW refer to the cooling water. So in this case, the cooling water is quite slow, yeah, compared to the flow of the ethanol. So in this case, it's a 0.603 meter per second. So this flow is in the annulus. So since while the velocity is lower than 1 meter per second, we will assume that we obtain turbulence, which enhance the heat transfer This is the assumption. Step 4, calculate the inside heat transfer coefficient. So the inside heat transfer coefficient meanings this is for the inner tube. So we calculate the Reynolds number first. Then calculate the Prandtl number. This is all available. Yeah, this is the inside diameter for the inner tube. Yeah, this is the what we calculate earlier, the actual velocity. Mu is given for the ethanol solution here. Cp 2.6. This is a viscosity divided by K. K is the here this thermal conductivity. Then we calculate for the heat transfer coefficient Hi. We get 996. Just follow. Next is the calculate the average cooling water temperature and the equivalent diameter of the annular space. This is for the cooling water. This is average 32.5. So DE is this is 102 minus 889. This is for the annulus diameter. Calculate the heat transfer coefficient. So use this equation to calculate the HO or outside heat transfer coefficient. Step 6, calculate the outside overall heat transfer coefficient. So due to the sagging problem, we will limit the pipe length to 6 meter only. 6 meter neck bend. So if it's more than 6 meter, then you need to do the bending. In the pipe to get the necessary heat, necessary area needed for the design, then calculate the surface area where the heat transfer occurs. So pipe length is 6 meter. So A naught pi D naught LP. So this is for the inner tube. Yeah, inner tube. This is for the inside diameter. This is for the outside diameter. So this is for the tube. So area is 1.676. This is for the inside diameter area. Sum the resistance and calculate the overall heat transfer. So using R for the resistance, using this value, we get this value for R. Then using the value of R to calculate the overall heat transfer coefficient, outside heat transfer coefficient. Step 7, calculate the area needed for the heat transfer and the number of bend needed. So since we will design the exchanger in a counter current fashion, we must calculate the log mean temperature difference. Now, with the delta TLM, we will calculate the heat transfer area needed. So in this case, Q equal to U not HE delta TLM. So delta TLM, we calculate draw first so that it's easy to understand. Identify the THO, THI, TCO, TCI. Then calculate for delta TLM. Since this is a 1-to-1, this exchanger, no need to do the correction factor. Then we can calculate the HE, heat transfer area. We are limited to 6 meter long pipe, and thus we may not have enough area to satisfy the required area needed for the heat transfer. 18.49 meters square. So we may need to bend the pipe. So how many bend that we need? So we calculate here. This is the heat area, heat exchanger area, calculate earlier. A naught is referred to the outside diameter for the tube, inner tube. So in this case, we need 11 bend for the inner tube to accomplish the thermal design. So thank you.